Hello, my name is Vincent Zhu, and this is my video lab report for Physics 2212 Lab 3, Magnetic Field of a Bar Magnet. The goal of this lab was to measure the magnetic field created by our bar magnet at certain distances in order to find the distance dependence. And we also wanted to attempt to code this as well. The three main principles that we used were the Biot-Savart law, which states that the magnetic field is equal to mu naught over 4 pi times 1 over the magnetic of r cubed times 3 times the cross product of mu and r hat times r hat minus mu. We also use the distance dependence law, which states that the magnitude of a magnetic field of a bar is equal to k times some constant k times r to the n. And lastly, we use that the magnetic field of a dipole on the axis is equal to mu naught over 4 pi times 2 mu over r cubed. So how do we do this up exactly? The first thing that we did was that we first figured out what magnetometer is on our phone by moving our phone both up and down, both vertically and horizontally, on a ruler lined with the magnet in order to find out where the magnet on our phone was. And we also made sure that we lined up with the Earth's axis because if we did not, then we also have to account for the fact that the Earth's axis on the Earth was also affecting the x-axis, which made this a lot more difficult. Once we found out where the magnetometer was, we then measured the distance from the magnet at which we produce certain microteslas. For example, like 70, 20, and 140. So this is the data that I got, and you can see that on average, we started, for example, the average R significantly went down, while we can see that as the R went down, the microtesla went up. And as you can see from this graph, which is auto-produced by our data, the line of best fit was y equals negative 2.845x minus 13.943. And the distance dependence n in this equation, is actually the ln of both sides, as you can see. And the distance dependence here is n, which is the slope, negative 2.845. As you can see here, if you take the ln of the initial equation that I stated in the second slide, you end up with ln of b equals ln of k plus n ln r. You also get, if you also set the krn equation equal to mu naught over 4 pi times 2 mu over r cubed, you can simplify out the r's. If we set the r's equal to 1, and you get mu naught over 4 pi times 2 mu. From the previous graph, the ln of k was negative 13.943. As you can see, it was the intercept. So here, so k would be equal to e to the power of negative 13.943, which is 8.8 times 10 to the negative 7. And lastly, if you plug that into this equation, if you just divide k by 10 to the negative 7, and you divide by 2, you get 4.4, and that was our answer. So we wanted to also code this. So the first thing that we did was I set my the answer that I got into the top, and mainly all I did was I created a function for the magnetic field, which all I did was I found r hat by dividing r by its magnitude, and ended up and the equation for b was simply what I used earlier. It was actually the first equation that I stated earlier: mu naught over 4 pi divided by the r cubed times 3 times the cross product of r and mu times r hat minus mu. And all this other code was mainly just creating arrows and scaling them to the best of my ability. As you can see here from this graph, from this picture, you can see that the magnetic fields on the axis are pointing in the same direction, but they're pointing the opposite direction when they're actually perpendicular, which is actually correct. And as you can see at the 45-degree angle, it's pointing to the top and the right. You can also see the data that I got from the 45-degree part when I was doing the lab in person, the physical part of the lab. And as you can see, the answers are slightly different, but that's okay, because there are sources of error when you're doing labs in person, and it's impossible to get them perfect. For example, it's impossible to completely mitigate the magnetic field of the Earth, which means that there were probably a little bit of error when I started. So what if I hadn't oriented my experiment to compensate for magnetic north? If I didn't have to, but if I didn't, then I'd have to account for the fact that the Earth's magnetic field was also in all three directions, and I have to make I'd have to correct them for every single direction, which would be a lot of work, and I don't think that was the best course of action. If I was to stick two identical magnets together, I think that my measurements would either double or square, and I think the answer was that they would square. Thank you.